let's continue talking about maximal ideals. I want to give some examples, but let me recap the definition quickly. Okay. So R is a commutative ring with 1. A proper ideal M in R, proper means that M is not equal to R. A proper ideal M in R is called a maximal ideal if there is no proper ideal that properly contains M. So you cannot have something that is strictly bigger than M but strictly smaller than R. There is no such ideal. So these are sort of ideals that sit like this. Here is R, here is M, and if you were to find something which is strictly in between, then that guy either better be just M or just R. There is nothing strictly in between. Okay. And though we proved this lemma, which tells you how to recognize a maximal ideal, M is a maximal ideal in R if and only if R mod M is a field. This triangle arrow means ideal. Yeah. So an ideal M in R is maximal if and only if R mod M is a field. And this followed from the fact that a ring is a field, a commutative ring with 1 is a field if and only if the only ideals in the ring are 0 and the whole ring itself, and then the correspondence theorem. So you can look in the previous video if you want for the proof of that. So, but given this lemma, you know an ideal is maximal if and only if when you quotient by it you get a field. That lets us give some examples. But I need an exercise, I suppose, to give the non-trivial examples, but here are some easy ones anyway. So examples. This lemma here already says that 0 is a maximal ideal in R if and only if R is a field. Because 0 is the only proper ideal, so it's a maximal ideal if and only if R is a field. What is the next ring that you want to look at? Z maybe. So maximal ideals in Z are exactly these guys. Pz, where P is a prime. Why? Because that's exactly when Z mod Pz is a field. Because we know Pz, P is a prime, that Z mod Pz is a field if and only if P is a prime. So 3Z is a maximal ideal, whereas 6Z is not maximal. Well, you can see that directly. This is multiples of 6. It is properly contained in the set of multiples of 3, and that's another proper ideal. So here is an ideal which is strictly bigger than that ideal, so that one is not maximal. But I claim that there is nothing strictly in between 3Z and Z, because Z mod 3Z is already a field. Okay. After that, maybe we should look at one variable polynomial ring. So let F be a field. And R equal to one variable polynomial ring. Then we shall see that the maximal ideals in R are the principal ideals generated by irreducible polynomials, where f is an irreducible polynomial. So we'll prove that if you take a polynomial ring in one variable and go modulo an irreducible polynomial, you get a field. At least you can see that this general thing will take some proving, but at least note that if you take one variable polynomial ring and quotient out by the ideal generated by x, sorry, my coefficients are in field, then you just get f. And this is because we have a surjective ring homomorphism from fx to f called evaluation at 0. Give me a polynomial, I send it to its value at 0. And the kernel of this map is, you can check all multiples of x. Verify that the kernel is all multiples of x. So if you have a surjective ring homomorphism from one ring to another, and this is the kernel, then the domain ring modulo the kernel is isomorphic to the image by the first isomorphism theorem. And since f is a field, this guy is a maximal ideal in fx. More generally, I'm saying that any irreducible polynomial will do. And if you want more examples, maybe we'll give a couple more. Let's go to two-variable polynomial ring. So for that, I need a little exercise here. Let R be the two-variable polynomial ring, where f is a field. So if you don't want to think about arbitrary field, you can take f to be real numbers or rational numbers or something. So verify that there is a surjective ring homomorphism from, I'm calling this alpha, from this ring, two-variable polynomial ring, to one-variable polynomial ring, defined by alpha of f xy equals f0y. So I don't evaluate both variables, I just evaluate the x variable at 0, and then I get a polynomial in one variable. And check that the kernel of this guy is all multiples of x. So that's then now, by first isomorphism theorem, domain ring, which is fxy, mod the kernel is isomorphic to fy. Let's do another one like this. Verify that there is a surjective ring homomorphism evaluation at 0, 0 from this two-variable polynomial ring to f, defined by evaluation at 0, 0 of f equals f at 0, 0. And again, by first isomorphism theorem, the two-variable polynomial ring, and the kernel of this guy. But there is this onto ring homomorphism and the kernel of the evaluation homomorphism is all multiples of x and y. So things that can be written as a x times a two-variable polynomial plus y times a two-variable polynomial. So by first isomorphism theorem, if you take the two-variable polynomial ring, which is the domain of this homomorphism, and quotient out by the ideal, then you get F. Okay, the proofs are very straightforward. Actually, this exercise that we did last time when we were talking about two-variable polynomials, this lemma here, it gives you a special case these things immediately. This exercise immediately follows from that lemma. In fact, part B we verified last time. Okay, so now that you have this, I can give you some examples of maximal ideals and non-maximal ideals in two-variable polynomial ring. See, part A of the exercise says Rxy modulo this ideal is, Fxy is isomorphic to Fy, which is not a field. There are plenty of things in one variable polynomial ring that are not invertible, like y. Yeah, so x is not a maximal ideal. Not a maximal ideal in Fxy. Whereas if you look at the part B, of exercise says that if you take the two-variable polynomial ring and quotient out by this bigger ideal, the ideal generated by x and y, then you just get the field F, which is a field, because F is a field. So x comma y is a maximal ideal in Fxy. And indeed, you can check rather easily that this ideal is strictly bigger. Like y is here, but y is not in here. And then the ring itself is again strictly because 1 is here, but 1 is not a multiple of x and y. So 1 is not in here. Yeah. So more generally, given any two elements, so let's take given any two elements in F, you can evaluate at AB, and that would give you a surjective homomorphism from the two-variable polynomial ring to F is a surjective homomorphism, and the kernel of this, we checked last time, is x minus a, y minus b, that ideal. So Fxy mod the ideal generated by x minus a, y minus b is isomorphic to F, is a field. So x minus a is a maximal ideal. In Fxy. So for every ordered pair of elements in F, there is a maximal ideal.